Hello guys, welcome to Intel Electronics. So in today's episode, let's take a look at how a car charger works. Now this was a very popular item back in the days when cars only have 12 volts accessory circuits and phones are usually Nokia that cannot be charged using a USB charger. But things are changing nowadays. Almost all brand new cars come with a built-in USB charger, and but still people are using these kind of external chargers for a lot of other purpose. Now chances are you still have one of these in your car, but you don't know how this thing works. Don't worry, in this video I will show you how exactly this thing works, and I will draw a schematics of it. I will completely reverse engineer this thing. So speaking of which, this particular charger, as you can see, is made by a company called Jabra, and they actually make a lot of Bluetooth audio accessories for vehicles. Now they don't make a lot of these chargers at all, but they do have a very similar and I think probably a very updated model of this USB charger. By the way, this particular model is discontinued and it is ESZ002, and it is capable of up to 750 milliamp output current, which clearly mentions that this thing is really old. Nowadays almost all smartphones uses at least 1 amps of current for its proper operation, for its proper charging. And this entire thing can operate on both 12 volts and 24 volts DC. And yeah, that's pretty much it. It's made by Jabra, and to open it, it's really simple. You just have to unscrew this top portion right here, and underneath here you will find a fuse. That is a good thing. And there is a spring underneath on which the fuse is sitting, so that is what creates this smooth kind of action. That action is possible because of the fuse. And let's see what rating this fuse has. If I can focus on it, it is a 2 amps 250 volts fuse. So 2 amps fuse for a device, yeah, it's pretty fine, no problem. And to take this thing further apart, you have to take this metal ring that is just used to hold the entire thing together. There is no screws or anything. As you can see, it is already starting to come apart, but using just some little force you can take the entire thing off. And inside it you can see pretty much very clearly that it has a very minimalistic components. And as you can see, this is a spring onto which the fuse is connected. And by the way, these are not anyway connected together. Oops, there it goes. And these two metal things are used for the negative contacts, and this is also what keeps this entire thing inside your charger, because it has this springy action. It actually friction locks to the 12 volt socket, so it does not fall apart very easily. So it's having multiple uses. And also you can see that only one of the two metal plates are actually connected to the ground. The rest is just for the holding this thing down. And let's actually take the circuit apart. Okay, that's really simple, because it's just, after all, entire mobile USB chargers like this one, including this one, is a buck converter. You can actually make one by yourself with really low components, but the efficiency will be a matter, because when you are actually making one, you have to do a lot of calculations to get the maximum output from it, maximum efficiency from it. If you only care about the output and just ignore the efficiency, you can make one really easily. But let's talk about this one, and this one uses very common IC, the MC34063A. This IC is actually really common for buck converters, and because this IC is a multi-purpose IC, it's not just a buck IC. This IC can be used for buck and boost operation, or even can be used for buck boost operation. So it is it's a versatile IC that way. And in here it is wired as in a buck configuration, but it can easily be rewired to form a boost converters, which is, you know, really a matter of only rearranging some of the components. The entire other things will work, and you cannot actually find the output voltage. That's the only issue that's going to be here. So let's take a look. At the bottom side there is no SMD components involved. You can see the IC MC34063A has two capacitors. This one is probably across the positive terminal. And okay, let me actually reverse engineer this thing, and I'll be back once I reverse engineer this entire thing. So okay guys, I now have completely reverse engineered this Jabra USB charger, and this is the result. As you can see from the circuit that it uses very simple components, and it was really easy to reverse engineer, and all this does is really simple. Before moving on to the operation, let me show you the data sheet. Let me turn the flash off. Let me show you the IC here itself. This is the IC that they are using. This is the 1.5 amps step up down inverting switching regulator, and this is the 4063 IC that we are having right here. And these are the features of this IC. I'm not going to show you the entire thing. If you want to read it, you can pause this thing. And this is the pinout for this. Okay, and let me tell you that after downloading this datasheet, I found that this circuit right here is an exact replica of what you can find right here. This is the step down configuration winding as per the datasheet, and this is what exactly this circuit really is. In fact, all it matters is just some component values are different. That is the only thing that is changed here. So let me tell you how this thing works. Even before that, let me tell you how a buck converter in common works. So let's say you want to reduce the input voltage. Here in my case, let me zoom down a little bit. In my case, let me tell you that, let me say you need to convert your steady 12 volts. Yeah, your steady 12 volts like that. That's the 12 volt. You cannot directly plug this 12 volts in to your phone, because your phone needs a much lower voltage, which is 5 volts for its operation. And there are a couple of ways you can actually reduce the input voltage. A simple method is by using a resistive dropper in series, just like connecting a 12 volt battery to a resistor and then connect your phone to the other side, low voltage. But the problem here is that you are wasting a lot of energy across the resistor as heat. Resistor can get pretty hot, and you're actually wasting a lot of energy, and this thing is not safe at all. You cannot guarantee that this thing works. This is a really simplest way this can be achieved. Instead, what we are actually doing is we are actually chopping down the steady DC volts that is right here. We are actually chopping it down. By chopping, I mean we are actually pulse width modulating the steady state DC. And because of that, let me take another paper, and you can see I was trying to draw this thing. Let me tell you that this using another pen, this was the 12 volts state. Okay, now let me tell you that this is for a 1 minute of time. Okay, so we are giving 12 volts for a 1 minute time, and it stays for 12 minutes, so like 1 minute. And now what I'm going to do is I'm going to chop this 12 volts at 50% duty cycle. That means the 12 volt is divided into a lot of different pieces like this. So it resembles a square wave, and this was also for 1 minute. Now, even though the voltage of each individual square wave is 12 volts, the entire device was on for half of the time. Let's say, this, you can actually see that this is on, this is off, this is on, this is off. What that means is a device is on for say 30 seconds and device is off for the rest of 30 seconds. So that is how this thing works, because in a 1 minute operation time, in a normal 1 minute operation time, you are getting the full 12 volts continuously for 1 minute, but in this case you are getting the 12 volts only for 30 seconds, not continuously but intermittently, and for the remaining 30 seconds your device is off, and because of that your device, the power consumption, the average power that your device receives will be low. So by adjusting the duty cycle, by duty cycle it means the on time, this is the on time, we will say it as T on, and this is the off time, T off. So the duty cycle means adjusting the duty cycle means adjusting the on time. So a higher duty cycle means a high on time and lower off time, and a low duty cycle means a high off time and a lower on time. So by adjusting the duty cycle you can get the required power you want. So that is the easiest way to reduce the output voltage. So by using some sort of mechanism to achieve this PWM chopping, you can then control the amount of voltage that you can get at the output by suitably adjusting the power, the duty cycle. So once that is achieved, you need a set of other components. You cannot just directly feed a square wave like this one to whatever load you are attaching. You need some other components, and that is where these extra components come to play. And in this case, this is the entirely simplest, this is the simplest of all circuit diagram for a buck converter. In fact, this entire circuit is only this thing, and the entire operation happening here can be divided into 3 sections. This here is happening at this point over here, and this over here is what is remaining over here. So what happens is that this IC, this MC340 IC, is actually a switching thing that actually converts this stable 12 volts into a lot of square wave pulses like that. So that is the purpose of this MC340 IC, and that is why I'm drawn it like that. So it makes the on and off kind of action. So what happens is that the 12 volt gets converted to a square wave, and because the inductor and capacitor is what smooths the square wave and forms a somewhat if I draw it, it will be like kind of like that. So it's smoothed out, it's like a filtering capacitor at the end of a rectifier. So this diode is a freewheeling diode that is used to prevent the back EMF. When the switch is open, the charge that is stored in the inductor will be huge and it needs somewhere to go, otherwise it will damage the entire IC. So once the switch is off, the entire charge that is stored in this inductor will flow through this diode so that it can operate in a stable manner. And when the switch is closed, the power can directly go from this side through the inductor, through the diode to the output. So that is the basic operation, and this is exactly happening at this point. The input here, let me show you that. The input here is going through a 0.1 ohms resistor, that is that one over there. So it is used as I think that is using as an inrush limiting resistor, and then it comes to this 100 microfarad filtering capacitor, smoothing capacitor, and then it goes through a 0.3 ohms resistor to the IC, and these are pin number 1, 7 and 8, and the pin number 1 and pin number 1 is a collector. There is an internal transistor inside. Let me show you that over here real quick. So this is how the entire thing works here. The pin number 1 is connected to this transistor, which is then switched to the ground. So your VCC is going through here, which is then turned on and off using this transistor, and that is how everything works. So after that, there is the 470 picofarad capacitor, which is used to adjust the frequency of operation for this internal oscillator over here. You can see the oscillator is connected to this capacitor, and after that the output from this is going straight. Output is coming from pin 2 and goes straight to the circuit that we just see over here. And this diode here is a 1N5819, which is a fast recovery time Schottky diode, 1 amp capacity, and that diode is this one over here. The inductor is pretty standard value. It is a 220 microfarad as per the data sheet, and that is over here, this one. This output capacitor is that one over here. This diode is just for the protection, an additional protection for the output device. And pin number 5 is actually a reference value, because that adjusts the switching frequency. If you look closely, let me turn off the light, you can see they're actually using two resistors. Oops, there it goes. Where is it? Let me find it real quick. I know this video is getting really boring, but still I lost it, I think. Anyways, okay, I got it. There it is. You can see these two resistors over here, the R2 and R1. That is the resistors. These two resistors are that one, and those two are that, and that's pretty much it. You can actually see that is used as the comparing point, so that it can adjust the switching frequency based on the voltage that is receiving at this point. So yeah, basically that's it. Okay, so now you know how a car charger works. If you have any doubts regarding anything that I said here, I know I made a few mistakes because this is microhenry, not microfarad, and there are some minor mistakes that I made. So you can, if you have any doubts regarding any of these things that I said, that I mentioned, like how this thing works or anything, if you have any doubts, please ask me in the comments below, or you can mail me. And right now, since I show you how it works, I'm going to test it for you. And since I don't have a car battery, the accessory socket, I'm going to use what I have here in my lab. It's a 12 volt 1.5 amps charger for something, I don't know, and I'm going to use a converter like that to attach it for it. So I hope so let's test this thing under load and see how this thing performs. I'm hoping that the green is the positive. The green goes inside that. Now there is no fuse connected in series with this thing, so if anything blows up, it blows up. You can see that happening live if anything happens. So I'm going to attach that to there. Maybe I can connect that later. For now, I'm going to need the USB tester, for which you can watch the video by clicking the link that will come now at the top I. So now I have turned on the power. I'm going to attach the white to the ground, and there it goes, it booted, and you can see the voltage is 5.38. Now let's test it by using a USB tester. I'm going to attach that to here, and it is now set to 1 amps of current, and I'm going to turn this thing on. without shorting anything if possible. Yep, even though it is rated for 750 milliamps, it is drawing 1 amps with a little bit of voltage drop is there. It's 4.5 volts, it's acceptable, but thing is that it can handle 1 amps. Let me check the inductor real quick. Yep, the IC is getting hot. I think it is not going to survive that. Let me see if it can survive the 2 amps. I'm going to switch it to 2 amp modes, and nope, there it goes. Just on 2 amps it doesn't even stand a chance. You can barely see. If I turn the light off, you can barely see that the voltage is dropping to around 3 volts. If I can show you that again, nope, it even booted. But the IC at 1 amps of current, the IC is getting really hot. It is really hot. I cannot touch that. But anyways, the fact is that it works, everything works fine. So yeah, if you have any doubts regarding anything that I said here, just ask me in the comments below. So that's it. That's about how your car charger works. Thanks for watching. See you in another video.